everyone, we're looking at question 2 of winter 2018 paper 419702. The question reads, state what is meant by the internal energy of a system. This is for 2 marks, pretty simple. You need to understand whenever you talk about the internal energy, which is the total energy, it's comprised of two things. Number one, the kinetic energy, and number two, the potential energy. Kinetic energy is from the movement, and potential energy is due to the attractive forces between it. So we will say it is the sum of the random distribution of kinetic energy and random distribution of potential energy. That is it. It is the sum of the random distribution of kinetic energy and random distribution of potential energy. 1 mark for this and 1 mark for this. Moving on towards B part, that says an ideal gas. This is such a huge hint that whenever you talk about ideal gas, and then you have talked about the internal energy in the first part, the internal energy of an ideal gas only depends on its temperature. This is something extremely important, that the internal energy of an ideal gas, it only depends on temperature. Moving on, they have given us a graph and we will see what it says. At point P, right here, the gas has volume 950 centimeter cube, pressure of this, and temperature of this. The gas is heated at constant volume, another hint, and 97 joules of thermal energy is transferred to the gas. Its pressure and temperature change so that the gas is at point Q. The gas then undergoes a change from point Q to point P, and then from point R back to point P. So it's eventually coming back to with the same point. Some energy changes that take place during the cycle PQRP are shown in figure 2.2. First part says, state the total change in the internal energy during the complete cycle of PQRP. Explain your answer. Now, we know the fact that it's going from P and it's traveling to R and then it's coming back to the same point. And you can see the temperature remains the same as well. So if the final, and we're talking about ideal gas as well, and we said that the internal energy of an ideal gas just depends on its temperature. So if the temperature is not changing, because we can say that the temperature increased here, the temperature changed here, but eventually it's coming back to the same temperature it started off at P. So temperature doesn't change, and when the temperature doesn't change, that means that the change in internal energy is 0, because the final temperature is equals to the initial temperature, and the internal energy of an ideal gas depends on temperature only. And I hope this makes sense. Moving on, B part, that says on figure 2.2, complete the energy changes PQR, so you just have to fill the dashes out. Okay. Let's look at the thermal energy transferred into gas, that is plus 97, work done from P to Q. P to Q is this. Now, they say the gas is heated at constant volume. The reason why I said this was such a big hint is because when we talk about work done for an ideal gas, it is work is equals to pressure into change in volume. Now, if volume is constant and volume is not changing, this value becomes 0, your work done becomes 0. They have said the gas is heated at constant volume. So when it's constant volume, which means there's no change in volume, which means work done is 0. So I can say work done here is 0. Increase in internal energy. Again, you need to be familiar with this one equation where internal energy is equals to the thermal energy supplied plus work done. Now I have my thermal energy plus 97, I have my work done plus 0, and so you will get your answer as plus 97. And that's it. And then let's look at change Q to R. Again, they have given us these two values. I can simply calculate this and I can get minus 42.5. Let's look at this final. Now, I do not know the thermal energy from R to P. Neither they haven't even mentioned it in the question. But what I do know is that the change in the internal energy is 0. So all of this should equal to 0. If I were to subtract these two, 97 minus 42.5, I get 54.5. If I get 54.5 plus, let's assume this as x equals 0, because we said the total internal energy is 0, so I just made an equation and I get x as minus 54.5. So you have to connect the dots from all the parts. Now we're left with the thermal energy. Again, you have this equation, you write minus 54.5 here. So if I were to write this down, let's write this in different color. So when I have minus 54.5 is equals to plus Q, which I have to find, I'll just take it Q, plus work done is plus 37, and then when I take this to the other side, minus 54.5 minus 37, I get a value of minus 91.5, and so minus 91.5 is my answer. And this completes the entire table and the whole question. So this is it for question number 2.